The following is presented by Ranco Incorporated and Paragon Electric Company, your power partners for appliance, refrigeration, comfort, heating, and cooling controls. Both members of the CB Group of companies. Ranco Incorporated has been manufacturing controls since 1913. In 1938, Ranco produced the original O control, which has become the industry standard for design, quality, and performance. Over 36 million Ranco O controls have been manufactured in the United States and in factories around the world. This video will cover 4 main areas. First, we'll discuss some important product features you should know. Then, talk about proper manual operation and installation of an O control. And finally, setup and adjustment. Common to all O controls is the use of a non-conductive, moisture-resistant Lexan cover. Covers built since 1980 are secured with a captive front access screw. Older models had metal covers with top access screws. Later models had Lexan covers in both beige and black colors that easily snapped on by design. Removing snap-on covers is done in 2 ways. On single controls, carefully pry from the upper left corner using a medium-sized flat blade screwdriver. On the dual control covers, remember to pry from the bottom left corner. Here you can see the new protective plate design, which has been in use since mid-1984. Compare this with an older model. The new plate completely covers the internal switch mechanism. The switch is covered on new units to stop improper manual tripping of the switch by prying. This practice often caused control damage to older uncovered models and should be avoided. In addition, the risk of severe electrical shock is present through improper manual tripping of the switch. Another key feature of O controls today is supercap. We'll talk more about this later in this program. A diagram on the cover plate shows the proper way to manually operate the control. This is done through the bellows lever tab, which has been lengthened on all O controls. This tab also lets you do a better job of troubleshooting. The control is designed to trip the switch from the bellows. Improper tripping of the switch by internal prying will alter the switch mechanism. In turn, control settings will be hard to maintain, so be sure to use the tab and don't pry on the switch. There is another way to safely operate the control manually. This is done electrically by placing a jumper across the switch terminals. Do this, of course, with the power off and with a properly rated jumper to carry the current. Remember, there are 2 proper methods for manual operation: tripping the switch through the bellows lever tab or installing a jumper across the switch terminals. When servicing a control, you may find that the cover shows signs of tampering. Often you'll find a notch or dent in the scale plate from prying. It's recommended that you change out the control in this case to save you and your customer an unnecessary emergency call. Also, controls with covers removed or signs of physical tampering do not generally qualify for warranty. Lastly, if the control has failed but shows no signs of damage, it may be the pickup. In this case, check the pickup as covered in the O&P service manual before installing a new control. When installing the conduit adapter, be careful not to damage the bellows hinge pin. A bent pin can cause the control to operate improperly. When wiring a control, there are some key points to remember. First, disconnect the power to the unit before and during installation. All wiring should conform to NEC and local codes. Finally, the electrical ratings listed inside the cover should never be exceeded. When mounting the control body, keep in mind these 2 points. First, be careful not to twist or strain the body during mounting. This may shift the calibration of the control. Second, if you use your own mounting screws, make sure they don't protrude into the control more than 1/8 inch. Any longer, and they may interfere with the control mechanism. When planning the installation of the control, there are two major areas you must consider: control positioning and vibration dampening. Positioning is important to prevent oil logging, while vibration dampening helps keep the control in service longer. In pressure applications, the control should not be mounted so oil will be drawn into the capillary when the compressor cycles off. Shown here is an example of a control and capillary mounted incorrectly below the connection. Generally, the higher the control is mounted above the connection point, the better. Shown here is an installation that allows the capillary to self-drain. Oil logging can happen because the inside diameter of the capillary is just under 1/16 of an inch. Oil trapped or logged there will reduce the control's response time to pressure changes and prevent true pressure from reaching the bellows. Ideally, both the control and capillary should be mounted above the connection point. But because this is not always possible, there is an alternative method. Here is an example. With this method, the capillary is routed up and over the connection point, then down to the control. Remember, the key in any mounting is to route the capillary so it self-drains. Finally, in some special applications where the control is subject to low temperatures, select a control with a male flare fitting and use 1/4 inch copper tubing. Used in place of the standard capillary, the tubing will drain easier if properly routed and lessen the chance of oil logging. All copper tubing will work harden and crack if flexed too much. That's why it's important to minimize capillary vibration to prevent control failure. And here's how. When installing the capillary, flex it as little as possible and avoid making any sharp bends. A 1-inch minimum radius is recommended. The capillary should travel straight from the connection point for a minimum of 4 inches. This is especially important on high-pressure connections. The capillary should be wrapped in 2 to 3 inch coils and secured to the compressor when mounting the control directly to the compressor. This allows both control and capillary to vibrate together. When mounting remotely, coil the capillary as needed for a vibration buffer. If the distance between coil and control exceeds 6 inches, secure the capillary to a stationary member. Also, secure any remaining length of capillary you have between coil and the compressor connection. If you coil the capillary, the coils should not touch. One method of separating them is to use a length of pipe insulation. You can use silicone glue to hold it to the coils. Excess capillary should be secured in 2 to 3 inch diameter coils as before. Also remember to allow some slack in the capillary. It should not be taut like a banjo string. The best way to check for excessive vibration is to watch the capillary while the unit is running. Also, you may run across special situations that will require you to adapt these guidelines to the installation. Now let's talk about a new approach Ranco has developed that helps reduce premature capillary failure. The Super Cap system is a capillary design that uses a unique vibration dampening cone and special low-mass, high-strength copper alloy tubing. The Super Cap system provides 10 times more vibration protection than controls with traditional capillary designs. We believe the Super Cap protection system is the best on the market. However, the effectiveness of any capillary system depends on how well it's installed. Remember, an improper installation will shorten the life of any capillary, including Super Cap. Most other manufacturers use a spring guard assembly that often is not as effective as Super Cap. Once again, Ranco's Super Cap is specifically designed to minimize control failure due to vibration. When setting and adjusting the control, be sure to follow the specifications given by the manufacturer for your application. You may also wish to refer to the Ranco O and P manuals as well. When adjusting an O control, you'll want to be careful not to run the pointers past either the highest or lowest marks on the scale plate. There are two reasons for this. Shown here is an O10 control with a close-on rise switch. If the range screw is tightened to completely compress the range spring, the bellows cannot move and the control switch will not close. Likewise, if the differential screw totally compresses the differential spring, the differential lever cannot move. This will cause erratic control operation. In practice, the scale plate is used as a starting point. Final control settings should be checked with a gauge set, and the system should be run through several cycles as a double check for proper operation. Let's go through an example and set up a typical control to show how cut-in relates to maximum refrigerated space temperature. We'll use an O10 control with a close-on rise switch where the cut-in and differential is indicated. Remember, differential is the difference between the cut-in and cut-out settings. The application we'll use is to control a system's temperature by sensing the suction pressure as would be typical of a reach-in display case. Here our cut-in is 37 and the differential 17. That factors out to a cutout of an even 20. When calculating the differential to use, remember the differential determines system runtime. Also, it's desirable to keep the system running as long as possible since starting causes the most wear. And the maximum differential is a factor of how low the space temperature can go and the limits of the compressor. Our display case has these specifications. It is self-contained, it is an R12 system, sensing for temperature control is by suction pressure, and it is equipped with a 15-degree TD-rated coil. You'll recall that TD is defined as the temperature difference between the refrigerated space temperature and the evaporator temperature. We want a case temperature of 37 degrees, with a maximum of 40 and a minimum of 34. This means, of course, that return air to the coil will vary from 40 to 34 degrees. So when the unit is running, the evaporator temperature will start at 40 and will drop to 19 degrees to cutout. The 19-degree cutout is determined by subtracting 15 degrees from the minimum desired case temperature of 34 degrees. Let's look at a chart for this example which plots the case temperature cycle based on these values. Note that the plot illustrates an acceptable cycle and that our average temperature is 37 degrees. Now we'll overlay the evaporator temperature. The effects of the 15-degree TD can be seen. Note that the evaporator temperature pulls down to 19 degrees to shut off. Next, since we're sensing the suction pressure, we can convert the evaporator temperature to pressure. Note how the cut-in relates to the maximum case temperature and the differential to the system runtime. Here, 40 degrees equals a cut-in of 37 psig, and 19 degrees equals a 20 psig cutout. Returning to our scale plate settings, we would set the control pointers as shown for the range and differential control settings we desire, based on how they relate to the charted information we've just seen. Here are a number of important points to remember when determining the lowest cutout settings. Cutout should never be lower than 20 inches of vacuum on R12 units. Single stage R22 or R502s never lower than 3 inches. 20 inches of vacuum is the lowest allowable control cutout setting. Remember, excessively low settings can damage compressors. And cutout is always cut in minus differential. A popular method to begin adjusting a control is to bracket the desired setting by raising the cut-in by about 5 psi and adding 10 psi more to the differential as starting points on the control. Adjusting the cut-in is done by turning the range screw, and to adjust the differential, turn the differential screw. Then, with these starting points set on the control, close the liquid line valve and allow the system to pump down. If needed, use the bellows tab to throw the switch open or closed to operate the control manually. Now open the line valve so the pressure will begin to rise back. As the desired cut-in pressure approaches, turn the range screw clockwise to lower the control set point and close the switch. Then, as the desired cutout pressure is reached, turn the differential screw counterclockwise to raise the control cutout and open the switch. On dual pressure O12 controls, the low pressure side is exactly the same as the O10 example we've shown you. This control also provides a high pressure cutout function. The high pressure scale plate directly indicates the high pressure cutout setting. Note too that some O12 controls are available with an automatic or manual convertible reset feature. The O11 control is similar to the O10 except for reverse switch action. The O11 switch opens high, closes low. Next is the O16 with a double throw switch. Its scale plate indicates the cut-in for terminals 2 and 3, which are the close-on-rise terminals. Terminals 1 and 2 are opposite. Their scale plate shows the cutout and differential similar to the O11 control. Let's briefly summarize what we've covered. First, when installing, avoid improper manual operation. Use the bellows tab or jumpers. Second, wire with care and follow all precautions, national codes, and control electrical ratings. Next, mount the control above the compressor connection point to prevent oil logging. The capillary should be able to self-drain. Be careful not to sharply bend the capillary and secure it to minimize vibration, either by direct mounting to the compressor or use vibration coils. Set and adjust the control using the recommended settings and proper methods. Also, be sure to confirm settings with a gauge set. And finally, remember that controls are like all refrigeration equipment. Take reasonable care during installation and adjustment, because doing so will help assure that your Ranco control provides long life and high performance. Thank you for watching. Now you know the Ranco O.